So, Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So, today our group Sahabat Hitam will present to you guys about our project in chemical thermodynamics. Right, so these are our team members. That is JAUHAR, SYAZWAN HAKIM, MUTTAQI, and myself, Muhammad BAIHAQI.
Our main industry is pharmaceutical industry. The pharmaceutical industry is responsible for researching, manufacturing, and distributing medicine. Its main goal is ensuring all healthcare products are safe, effective, and of high quality. Key manufacturing steps include raw material, preparation, separation, and packaging. Ultimately, thermodynamics play a critical role here by managing crucial energy transfer and heat control. The pharmaceutical industry is vital because it improves public health, support economic growth, and drive innovation. Large-scale production ensure medicine remain accessible globally. Furthermore, thermodynamics play an essential role by controlling temperature-sensitive reaction and optimizing overall manufacturing conditions to maintain strict product stability. Thermodynamics is directly applied across key pharmaceutical processes. For example, chemical reaction rely on enthalpy to control temperature, while distillation use vapor-liquid equilibrium for solvent purification. Additionally, phase equilibrium drive crystallization for drug purity, and thermodynamic cycle ensure stable product refrigeration and storage. This process flow diagram highlight the manufacturing journey of oral solid dosage from like ibuprofen. It start with milling and blending the active ingredient and excipient into a granulator. After drying and post-milling, the uniform granule move into a hopper and feed frame, where a tablet pressed from them into final tablet before coating and packaging. To conclude, thermodynamics integrates seamlessly across pharmaceutical manufacturing. The first law governs energy conservation, while the second law reduces energy loss to improve overall efficiency. Additionally, phase equilibrium drive separation and heat transfer principles strictly protect final product quality, ultimately ensure efficient, stable, and completely sustainable manufacturing.
Now I will talk about one of the key processes in the pharmaceutical industry known as the freeze drying, or also known as lyophilization. In this process, the first step is freezing. The formulation, in this case drug plus excipients in water, is cooled into a solid frozen matrix. Ice crystals form and grow, leaving a porous network in the unfrozen matrix that later allows vapor to escape. In this process, the conditions for temperature are negative 40 degrees Celsius to negative 50 degrees Celsius, and the pressure is atmospheric. Second is the process called primary drying, or also known as sublimation. Under deep vacuum, frozen water sublimes directly from solid to vapor by passing the liquid phase. This removes 90 to 95% of total water content. In this process, the temperature is between negative 40 degrees Celsius to negative 20 degrees Celsius, and the pressure is 0.05 to 1 millibar. Last but not least is the secondary drying, also known as desorption. The remaining bound water absorbed to the solid matrix is dissolved at a higher shelf temperature under continued vacuum, reaching final residual moisture below 1 to 3%. In this process, the condition for temperature are 20 degrees Celsius to 40 degrees Celsius, and the pressure is low vacuum maintained. Now I will talk about the thermodynamic analysis of the freeze drying process. In terms of energy, for the first step, which is freezing, it is exothermic, since the latent heat of fusion is released as water crystallizes, which is heat of fusion equals to negative 334 kJ per kilogram, is removed by the refrigeration system. For second step, which is primary drying, it is endothermic, since sublimation requires latent heat, which equals to 2838 kJ per kilogram supplied by shelf heating. Without it, the product self-cools and drying stalls. Last but not least, for the secondary drying step, it is endothermic because dissolving bound water from the solid matrix require energy beyond the heat of vaporization, since hydrogen bonding to the matrix must also be overcome. Net process overall, it is endothermic. Continuous heat input is required throughout drying, while latent heat is removed again at the condenser, which is known as desublimation. For the equilibrium, sublimation is a solid vapor phase equilibrium. Net mass transfer occurs only while chamber pressure stays below the equilibrium vapor pressure of ice at the product temperature, a positive driving force. As chamber pressure approaches the equilibrium, the actual pressure of ice and the driving force approaches zero, and sublimation effectively stops. Operation must stay below the triple point, which is 0.01 degrees Celsius and 6.11 millibar. crossing into the liquid region causes meltback and causing the cake to collapse. Secondary drying is bounded by the desorption isotherm of the dry cake. Residual moisture only approaches an asymptotic equilibrium value. Complete 100% water removal is thermodynamically unreachable. Key point is the extent of ice to vapor conversion is capped by phase equilibrium, not only by how much heat is supplied. Now for the operating condition. For temperature, raising shelf or product temperature increases the equilibrium vapor pressure of ice exponentially, widening the driving force and the speeding sublimation. But product temperature must stay below the formulation's collapse temperature, also known as critical temperature, or the cake will melt back. For pressure, lowering chamber pressure widens the gap between it and the equilibrium vapor pressure of ice at a given temperature, accelerating sublimation, but is bounded by condenser or vacuum pump capacity and the risk of choke vapor flow at very low pressure. Design principle: push temperature as high as the collapse limit allows and P as low as the equipment allows. Together, they maximize sublimation rate without compromising the product. As we can see in the graph, the vapor pressure rises when the product temperature increases. Now we move to our second chosen process, which is tablet press. So what actually happened in this process? We start with a granulated powder mixture containing our API, and then this powder mixture will be fed directly into a die cavity. And then two steel punches, an upper and a lower punch, converge rapidly to apply an immense compressive force, condensing that loose powder into a highly dense, uniform and structurally solid tablet. And then we move to the thermodynamics. For the first one, when those steel punches slam down, they are performing an immense mechanical work denoted as W on our system. According to the first law of the thermodynamics, which is delta U equal to Q plus W, a substantial portion of this mechanical work is dissipated as heat. And then this will cause a rapid and localized spike in temperature within the tablet matrix, often rising by 10 to 30 degrees Celsius within millisecond. Now we move to the second thermodynamic analysis, which is equilibrium and phase considerations. The intense thermodynamic stress can actually disrupt the crystallatives of the drug. We often see a partial phase transition on the particle surfaces, shifting them from a highly stable to a highly energetic metastable amorphous state. While an amorphous state can temporarily improve the dissolution rate of a drug later on, during manufacturing, it introduces unpredictability because the system is constantly trying to revert back to thermodynamic equilibrium. Furthermore, we have to look out for local melting and solid-liquid equilibrium. Because of that rapid localized temperature rise we just discussed, the micro temperature can easily approach or even exceed the melting point of low melting point drugs. And then this brings us directly to our next discussion, which is the effect pressure and temperature. So, we're choosing ibuprofen as it is really difficult to compress because it has an incredibly low melting point, only about 75 degrees Celsius. And then increasing the compression pressure puts more mechanical energy into the system, and then this will directly increases the internal heat generated. When temperature is high, the drug will experience premature softening, becomes sticky and adhering to the faces of the stainless steel punches rather than cleanly ejecting. And this is why it is important to be strictly climate controlled in terms of both temperature and humidity to prevent the system from crossing its thermal threshold.
Alright, so next, the role of thermodynamic in industry. Alright, so the first role is drug discovery and molecular binding. For a drug to spontaneously bind to a target disease protein, the change in Gibbs free energy must be negative. This dictates a molecular tug of war between enthalpy, the strength of the chemical bond, and entropy. Next, the second role is managing polymerism and drug stability. Many drugs can crystallize into multiple structural arrangement called polymorph. If a company accidentally manufactures a less stable version, it can then transform on the shelf, altering its solubility and making it dangerous. Thermodynamics allow engineers to map phase diagram to lock in the correct crystal form. So moving on to the next rule is optimizing solubility and bioavailability. If a drug can't dissolve, it can reach your bloodstream. By understanding the thermodynamic of mixing, scientists can trap drugs in a disorder amorphous solid dispersion. Their higher free energy drive faster dissolution. Finally, the fourth or the last rule is pharmaceutical engineering and scale-up. During manufacturing, thermodynamics define the solubility curve needed for purifying crystals, mass vapor liquid equilibrium for distillation, and utilize the precise triple point of water during freeze drying to supplement ice directly into vapor. So the example, we give you three example: crystallization, freeze drying, and distillation and extraction. So lastly, for the conclusion, we can conclude that thermodynamics is the non-negotiable framework that ensures every medicine is potent, stable, and manufacturable at scale. It's help in the pharmaceutical industry to make a drugs and control it so that it could not become bad things. That's all from us. Thank you very much.